Hello, everyone. Thank you for joining. The question of the day is as follows. The heat capacity of water is much higher than the heat capacity of air. Calculate the temperature change when 10 kilojoules of heat is transferred to 1 cubic meter of water or air. The density rho of water is 1 gram per cubic centimeter and density of air is 1.2 milligram per cubic centimeter. Okay, first let's recall what heat capacity means. If you look at the unit of heat capacity here, it's joule per mole per Kelvin. So it is energy per amount of the substance per temperature. In other words, the heat capacity of a substance basically tells you how much heat you will need to raise the temperature by 1 Kelvin for 1 mole of substance. In mathematical expressions, we can write this as Cp equals Q heat divided by mole divided by the change in the temperature. This, if you rearrange this equation, then it's the same as saying Q is equal to Cp times mole times delta T. In other words, the total amount of heat transferred is going to be equal to the heat capacity of the substance times the mole or the amount of the substance times the temperature change that the system undergoes. Also, if you rearrange this one more time, you can also express it in terms of the temperature change, delta T. Delta T is then equal to Q divided by Cp divided by the mole of the substance. Here in this question, it's asking about what is delta T. So we better use this form of the equation and basically try to figure out what are these three terms so that we can compute for delta T. Fortunately, we are given the Q, which is 10 kilo, given as equally 10 kilojoule for both water and air. We are given the two numbers of Cp for water and air, but we are not given the moles of each substance directly. Instead, what we are given is the volume of both substance and the density of both substance. Now, here I want you to pause this video and think about how you may be able to get the moles of each substance given the volume and the density. Let's pause here and think about it. Yeah, you can get the moles. First, in order to get the moles, you have to first know the mass. And the mass can be obtained from the density and the volume. And if you recall what the density is, which is mass divided by volume or mass per unit volume, it's pretty straightforward, right? The rearrangement of this expression of density is going to directly give you that mass is equal to density times volume. So you can calculate that for both the water and air since we know the volume and we know the density of each. The second one we need in order to calculate mole out of this is the molecular weight. Molecular weight. That is how many grams of the substance there will be if you take 1 mole of each substance. And so you can do that for water and you can do that for air. Water, it's 2 of H and 1 of oxygen atom. So it basically, the molecular weight becomes 2 times the atomic mass unit AMU of hydrogen, 1 gram per mole, plus 1 times the AMU of the oxygen. Therefore, you get 18 gram per mole as the molecular weight of water. For air, we have to take the average molecular weight of the component molecules. Air is generally considered to be made up of 80% nitrogen and 20% oxygen. So then basically the average molecular weight would be obtained by 0.8 times the molecular weight of nitrogen plus 0.2 times molecular weight of oxygen. And that should give you 29 gram per mole. Once you know the mass and then the molecular weight of each substance, then you can calculate the mole. The mole is basically mass, gram, divided by the molecular weight, which is gram per mole. Then you see that in the unit, this gram cancels out, and you basically end up with the mole only, and that's what it is. So okay, so we have the roadmap, right? So if you have the mass, if you have the density and volume, you can calculate the mass and you can calculate the molecular weight, and from those two numbers you can calculate the mole of air and water. Why don't we pause here and you guys calculate the moles of water and air here? Okay, done that? Well, if you did the calculation correctly, you should have gotten the mole of H2O as 5.5 times 10 to 4 mole, and then molecular weight of air should be 41 mole. Okay, so now let's pause this video again, and now let's compute the final answer for delta T. Again, coming back here, delta T is the heat 10 kilojoule divided by the heat capacity and by the moles of that substance. We just calculated those moles here. So you can calculate, now you're ready to calculate the delta T. Please pause the video and do the calculation. Okay, how did it go? Well, the answer is the delta T of H2O should be 2.4 times 10 to minus 3 Kelvin, and delta T of air should be 12 Kelvin. This is not surprising. If you come back here and look at the equation, delta T is going to be less for a substance that has a higher CP and also for higher moles. It turns out in this question, the CP of water is about 4 times higher than that of the air, and the moles of water is about 1,000 times that of the air. Therefore, you expect the delta T of the water to be 4,000 times less than the delta T of the air. Okay, I hope this helps. I know this is my first video, so not very nice or anything, but I just hope that this prompted you to wake up and do one problem today. And so if you did, congratulations. See you soon.